Hi everyone, in this activity we're going to be looking at fundamentals of functions in R. So just like usual, we'll use R Markdown to complete this. So what we'll be looking at learning is how to create our own custom R functions, and separately how we can use what are called conditional statements. So sometimes we only want to execute portions of code given that a certain condition is true. And then we'll also look at how we can use what are called warning and error messages inside our own custom R functions that we make. So a great aspect about R is that not only do we get to use functions that come pre-bundled with base R, or to use other people's packages that they've created with their R functions in them, but the developers of R and people at RStudio have made the process of creating our own functions, our own R functions, not too bad either. So this allows us to bring our own approach, our own pieces of flair into our R coding that we get to use. So functions allow us to tailor our own R experience, which is nice, but they also allow us to write more concise code, so to have less lines of code to achieve our task, and also to be more reproducible in the code that we use. So facilitate the process of someone else reproducing our results, or our future self to reproduce results that we obtained previously. Functions that we make in R can make both of these things easier to achieve. So one of the main reasons to write an R function and to create it is to avoid copying and pasting repetitive code many times. So maybe, for example, let's say I had 3 data sets. Data set 1, that had some values. Data set 2 and data set 3. Let's say I had these 3 data sets. And maybe I wanted to drop a column, the last column from the data sets. Let's say that. So and only keep first 2 rows. Let's say I wanted to do something like that. So I could do that with the select function to drop the last column, which in this case is the second one, and then only keep the first 2 rows. I could use slice head n equals 2. So I could copy this code if I wanted to do it for all 3 data sets and paste it and tweak these values here. And this would work. Okay. Alternatively, though, because there's the potential to accidentally forget to update things in the copy and pasted code, or let's say maybe the last part, oh, I want to print the first 3 rows, but only drop the first column, and just drop the first column instead of the second column like that. So I could spend time updating that. Maybe a more concise way to achieve the same type of goal is to write a function drop calls keep rows. Okay, so I could write my own function that sort of like achieves this same thing. So we can say which columns to drop, which rows to keep. So maybe drop calls, keep rows. And then the first argument will be the data. Or maybe we'll just call that X. We then could do it like this. So drop calls, keep rows. So this would be how we could use a function, for example, to make this process more reproducible. So instead we could say create function to drop the last column, or to drop columns of a data set and only keep some rows. And then instead of copying and pasting this code, we can apply this function to the data sets here. Keep rows equals so now if we want to end up doing something even more complex, we only have to update it in this one function call here, in this one function definition here, rather than having to do it in the 3 spots. Like let's say we also want to sort the data set by some variable. We would have to do that 3 times up here. Like we want to arrange by X. And we'd have to do that in 3 spots, whereas with our function, we only have to do that in 1 spot. And we just keep the call to the function down here. So this already starts to save us a bit of code as the thing that we're trying to implement. Oops, we need this. Let's see outside here. This already starts to save some code writing as our code gets more complicated that's going to be inside our function. Oops. Oh, because we dropped the columns here, it doesn't like, this one would be like arrange by Y. I think this would work instead, yeah. Okay, so that's just one example of how copying and pasting code can be replaced with using a function instead. So these functions, by using that instead of copying and pasting, can save ourselves, our future selves, time and effort, because it can be easier to figure out what your code's doing for one thing, because it's shorter or more well documented. And it also helps others who are trying to use your code. Functions make it easier to understand what's going on in your code. It makes your code shorter and also less prone to bugs. So having a workflow where you do a lot of copying and pasting is not ideal of code, and then just updating it slightly depending on what you're trying to do, versus using functions in our workflow. Has a much more tidy, organized aspect to it. And so everybody's happy. These little monsters in the picture are happy. Okay. So yeah, emphasizing some of the points I mentioned. When functions have a descriptive name, that can help communicate what your code's doing. Having functions in your code, using those when possible, also reduces the chance of bugs or mistakes in the code. because you don't have to update the code in as many spots as you try to change it or want to change it, as compared to a copy and paste approach. So we'll look at how we can create some functions in R today in this activity. And we'll start by loading some packages. I'm going to start with that. So you actually don't need the tidyverse or the string R package to create functions in R. You only need base R. So you don't need to load any packages at all, but we're going to load these just to complete some examples. Okay, to showcase how we can use functions in R. So let's start with a somewhat silly function. It's a little bit simplistic, but it's a good starting point to understand how we can make functions in R. So we're creating a function here using this code called MySum that calculates the sum or addition of two numbers. So let's copy this code exactly. Okay. So MySum can add two numbers and returns that result. So notice in R, the general syntax is function name, which we get to pick. It just has to follow R's naming conventions. That is the same as the naming conventions for objects in R. So underscores are fine. It's case sensitive. So MySum with a capital S is different than MySum with a lowercase s. Then we store that and then say function. And then in parentheses, we give the arguments or inputs of the function that will be used in the code. And then in between curly brackets here, we put all of the code, which can be multiple lines of code. This is just has one line of code to be executed based on the inputs. Okay. So in this case, it returns the value equal to the sum of number 1 and number 2. So you may notice that we don't specify the exact type of each of these inputs. So we descriptively named them number 1 and number 2, but R would let you try and give a string to this function. And it won't, it'll just keep on going with the code and try to add them. Okay. But it'll get to that point where it tried to add them, and then it throws an error. Okay. So some programming languages, like C++, require an explicit designation of the type of the inputs for functions that you define. So like in C++, when you make a function, you have to say int number 1, saying that number 1 is going to be an integer, and numeric number 2. You have to say that that's specifically going to be a double numeric, something like that. But R is much more flexible. It would allow this to be a list, a single number, a string. It allows anything for each input, and will just try to execute the code as it can with what it's given. Okay. So that's a bit unique in how R is structured that way. So let's try to calculate the sum of 13 and 1989. Let's see how that goes. Say the number 13, 1989. 2002. It's a great year. And let's see, what do we think will happen when we try to add NA in 1989? Will we get NA? Will we get 1989? or will we get something else? So we get NA. Maybe not too surprising, because if we take NA ourselves, add that to 1989, R gives us a missing value right back. So notice that this is a simple function in that it cannot handle missing values very well right now, but we could customize it further to handle that. So talking about some best practices when creating R functions. So just like when we name our objects or create our objects or data sets, we want to name them descriptively and consistently. So a good function should be named descriptively, in that the name tells us what the function does, but also concisely, in that the name is not super long. So for example, naming a function that calculates sum of two numbers, very descriptive, but not a very good name. It's far too long, right? So being descriptive is good, but we want to be concise at the same time. So MySum, for example, yeah, is fairly descriptive, but concise as well. Okay. We also want to name inputs or arguments to the function descriptively as well. So in this case, in the MySum function that we created, it's helpful that we named the inputs number 1 and number 2. That can help us understand what input value is typically expected there. In this case, it's signifying, hey, that's supposed to be a number, not a string. Okay. Although, notably, and Hadley mentions this in his book, when you have a relatively simple function, like this one that just adds 2 numbers, it's okay also to just call this like x and y, just because the function is so short. It might not matter as much as a more complicated function, where it's important to really be descriptive in the argument names to help the user or your future self. So going back to Dr. Alison Horst, who made this image showcasing different naming conventions in R that you can use, or other programming languages for that matter. Camel case, I would say, and or snake case are the most commonly used naming conventions for R functions and R objects. Big thing is to be consistent. I personally really like camel case, so I tend to use that. I think snake case is great too, and honestly still use that occasionally. Either one's great, but yes, R is case sensitive, so it differentiates between camel case and all lowercase versus camel case with a capital C. It'll differentiate between those two objects or functions. Camel case and snake case are great because many programming languages would accept those naming conventions, like C++, SAS, R, all take snake or camel case as valid variable or function names. Kebab case is valid in R, so words separated by dashes, but many other programming languages don't like the dash in variable names. So this is not very commonly used, and I would advise against it, even though it does work in R. So another way we can be consistent or helpful in how we name our functions is to be consistent in how we name them. So if we create multiple functions that are related, we could use a common prefix, so start of the function name, to signify the purpose of the function or how it's related to other ones. So here's a bad way to name functions, for example, calling it just fun1 for function1 or fun2. Okay, not descriptive. We have to actually read the code and understand what it does in order to get a grasp of what this function's purpose is or what it achieves. Instead, we could say compute sum, compute diff, to say it computes a sum or it computes a difference, and then call the arguments number1 and number2 to indicate that the inputs or arguments should be numbers. This may sound very clear or may seem obvious that of course we should name functions this way, but sadly I think it's fairly common, just because sometimes I think people are excited just to get coding and they know how to do things, so they want to keep powering through their script. So they name things in this convention like fun1 or variable, or a common one you see is foo, F-O-O. When people don't want to take the time to name something, they might just call a function or an object in programming foo, which is meaningless. So please don't do that. I'll always try to name your functions descriptively when possible. Helps your future self again and others using your code. Some other things to look out for when creating functions in R, and this one's not as much of a concern when you're a beginner, just because it's less likely to cause issues, but it's best practice though, is to not overwrite already existing functions or special objects in R. So R allows you to overwrite base R functions when you're trying to create your own functions or objects. So for example, the mean function already exists. Okay, we can calculate the mean of numbers 1 through 5, but R does allow you to, and I wish it wouldn't, it does allow you to create your own function called mean, the same exact thing. And like, let's say it just returns the sum of the values of X. R allows you to do that. And so now the mean is not the same anymore. See, and this is problematic because maybe you forget this and later in your code try to use the regular mean function, but you forget that you overrode it with something else. Okay. So try not to override already existing functions in R. You know, most people don't do that with mean, but some common ones I've seen before is overwriting the value capital T. So capital T represents the value true in R, a Boolean value, and R will allow you to overwrite this value. But it's important because sometimes you might want to check if something is true. Like, is this a missing value? We might want to check if that's equal to the value true. So we don't want to overwrite this necessarily. We want to keep that as it is and leave it be in R. Some other ones that are less commonly or less likely to cause issues, but still good to avoid naming them, overwriting these names, is df, which stands, it's a base R function that gives you the probability density function for the F distribution. Okay. So commonly people like to overwrite this df value because data frames are a common object we work with in R. And so short for data frame, someone might call it df. I've seen a lot of people chastised on Stack Exchange posts for doing this in their code that they posted, trying to get help. I really don't think it's a big deal, but just something to be aware of, that maybe, you know, I would avoid it. But again, I don't think it's a huge deal that you overwrite this value. Same with DT. Sometimes people like to overwrite that because it's data table. like a table of data, you call it DT, but that's the probability density function for the student's t distribution. So we probably want to avoid overwriting it, just as a heads up. Those are some common ones that we want to leave be and avoid using those variable or function names. Oh, and lowercase c is the combined function. So that one's tempting because sometimes you create a variable called a, b, and c, but you want to leave c alone because we use it to create vectors in R. Okay. All right. So in addition to naming our functions in a descriptive way and naming the arguments or inputs in a descriptive way, it's also good to write comments to indicate that we're creating a function or the purpose of our function. So I think this is best to do right in the line immediately above where you start to create the function. And then if you have a longer function, I think it's best practice to add comments or include those inside your function as well, indicating what pieces of code do. There's, the number of times that this has helped me when I come back to code that I've written a while ago, it's too many to count. And also, again, as I have emphasized, sometimes other people will end up trying to use your code, and so comments can really help them understand what you wrote. So let's take a look at this block of code here. And there's some new functions in here, but let's try and take a look at it for a minute and add some comments to indicate what we think it's doing. So maybe pause the video and take a minute or two to read through this function and try and give your best guess or estimate about what this function is doing. So this function is similar to the sum function we created before, which had two required arguments in that you had to give a number 1 and a number 2 if you call this function. It does not let you, if you try to just give one number, it won't let you do that. It'll throw an error saying, oh, where's number 2? That's a required argument. And this function now has a third argument that is not required. We give it a default value using a single equal sign in the function definition. So what this does is it defaults to assuming remove.na is true unless the user who calls the function specifies otherwise. So let's try and use this function on some values just to help us think about what it's doing. So if we calculate the sum of these numbers, oops, got to define the function first here. If we calculate the sum of these numbers, oops. Let's say, yeah, we'll do the same numbers again where we had 13 and 1989. We get 2002. So that's still the same as before. Now, what if we have a missing value? Now it's removing them. So it's not returning NA anymore. It's removing those values. Okay. What if we set remove.na to be equal to false, though? See, that's where we can see we can override that behavior and set that argument equal to being false. So what you'll see here is that you can call this function and specify some of the arguments by name, or you can just give them separated by commas. And what R does is if you don't specify specifically what the function argument name is, it assumes the same order as in the function definition. So here 13 is the first thing given, so it assumes that applies to number 1, NA is applying it to number 2, and then this one we specified by name. So there we can see how that new function works. So in this code, what's happening, which we'll look at if and else's a little bit more in this activity, is it works its way down, starting top to bottom. It sees if NA is true, it will execute the code in between these two curly brackets, if this is a true value. Otherwise, if this is false, it executes the code instead between these two curly brackets. So this is called an if-else, and they're commonly used across many programming languages. So then after it evaluates either of these two blocks of code, it returns the calculated sum. Within this remove.na portion of the code, it's using this if-else function, which is a separate concept from this if and else here. So the if-else function, which you can look up the help file for, and then we're looking at the base one. The if-else function takes 3 arguments itself. A Boolean or logical value is the first one. The value to return if the first test or condition is true is the second argument. And then if this first test or condition is false, it returns the value of the second, or the last argument here, the no. Okay. So in this case, when number 1 is missing, this returns 0 into calculated sum here, into this first number to be added. And if this is missing, if it is .na, if that's false, if it's non-missing, I should say, it actually returns the number itself. It does the same thing for the second number. So this is how we can add this option to remove NA values when we add these two numbers here. Let's try looking at these 3 functions now. So let's determine what we think the purpose is of each of these and then propose some better function names. So maybe pause the video again for a minute or two and try and guess what these functions are supposed to do, what their purposes are, and then maybe think of better names for them. Let's start with F1. Okay, so talking about F1, here the arguments are string and prefix. So F1 returns a Boolean value, a true or false, depending on if this thing is equal to this thing. So since it's 2 equal signs, it's checking equality and not doing assignment. So this is checking the equality of 2 strings. So for example, if we have GVSU and we check if that is equal to SVSU, that returns false. Those are not the same 2 strings. If we check GVSU equals GVSU, that returns true. Okay. So we have 2 strings in this equality, checking of equality, one of which is just given in the function as an input, the prefix, and the other which is calculated based on the input string and the length of the prefix. if you're not familiar with what a prefix is, maybe Googling it might be helpful. It's a word or a set of letters at the beginning of a word. So like anti-establishment, anti is a prefix. Pro-democracy, or what would it be? Proactive. Proactive, pro would be another example of a prefix. Okay. Another helpful thing to think about these functions is to look at the help files. So there's two functions in here that are a little bit new. nchar, which gives us the number of characters in a string. Okay. Sometimes it's helpful to look at the help file at the bottom of it in the examples section. Okay. So here, for example, we can see nchar gives us the number of characters in different strings. String sub gives us a substring of a given string, where we need to specify the start position and the end position of the substring that we want. So here there are 4 characters. So we're saying start at the first character and go until the second character and return those consecutive strings. And we could also get the last 2 characters. Okay, so the string sub extracts a substring in R. The -1 in the example file, so R gives capital L next to integer values sometimes, just to emphasize that it's an integer, not a double. So it's an integer 1, not a 1.0000 number. Okay. The -1 here is saying the very last character. So the default of this is to start at 1 and go until the end, the last character, which gives you the whole string, always. Okay, so keeping that in mind, what the nchar function and the string sub function does, this is extracting a substring from this input that starts at the very first character and goes until the number of characters of the prefix. So this allows us to check if a given string starts with a given prefix. So maybe we'll call the function starts with. And we'll showcase some examples here about how this works. So we can check if the string antihero does that start with anti. And we can also check if antihero starts with hero. So this will return true. What about this one? This will return false, because even though the string contains the prefix, it does not start with it. And that's where this part just checks if the string starts with that given prefix. So that was this function. So we can add comment, create. Now let's look at this next function. Let's think about what this one does for a minute. So one thing we can do is make x a vector of the numbers 1 through 5. And then we can see what this code does. So we can see it returned all the values except for the last one. We can also make x a vector of strings. And if we run that code again, it drops the very last entry of the vector. What if x is just a single value? What will our function do? Let's see. Oh, I had an error actually. Let's try to define our function here. If we try to call our function, again, it drops the last entries of the vector. You can see it drops that last entry of the vector. And then if we try to just give a single value, it returns the value null. Right. So this function drops the last entry of a vector. Maybe we'll call it drop last. Maybe we'll call this one starts with a prefix, to be more descriptive. Okay. We'll update the function names here. The last function here, can try and read this and see what this function is doing. So this function f3 is calculating what's called the harmonic mean. So traditionally, when we've used the mean, we've been talking about the arithmetic mean, summing the values and dividing by the total number of values that we have. There are actually many other means or types of measures of center that can be used as well. So the harmonic mean is one example of that, in which you take the reciprocal of each value, the arithmetic mean of those reciprocals, and then the inverse or the reciprocal of that whole thing, that is your harmonic mean. So a better function name probably here, harmonic mean, just like this. And you can see how that is similar to the regular mean, but not exactly the same. Oops, I have to define the function first. And actually, yeah, they can be quite different depending on the vector of numbers that you're working with. Right. Let's see. So another type of mean besides the harmonic mean and the arithmetic mean is the geometric mean. So the geometric mean is calculated as the product of the values to the 1 over n power. Or in other words, the nth root of the product of all the values. So we could actually multiply all of them out and then put that to the 1 over n power. Alternatively, it can be shown to be mathematically equivalent to calculate the geometric mean as the arithmetic mean of the natural log of the numbers exponentiated. So e to the power of the arithmetic mean of the natural log numbers, the natural log of each number. Let's maybe try the product version of it, but you could try this one as well if you're familiar with the natural log. So to do this in R, for the exponentiation, there's an exp function in R. If you want to go that route, oops, exp. And then there's also a log function, which does the natural log by default. So you can try those if you want. We'll try it with the product and the nth root in this part here. So let's see. Start with this code. We'll call it geometric mean. And we're going to take advantage of this prod function, which works very much similarly to the sum function, in that it calculates the product of all the entries of a vector, rather than the sum of all the entries of a vector. And then we can also set a number or vector of numbers to a specific power using the caret symbol. So we want to calculate the product of all the numbers and then put it to the 1 over n power, where n is the number of values. So first, let's maybe calculate product. We can do that using prod. We'll call this x's maybe, because it's multiple values. Maybe we'll just call this values. We'll calculate the total number of values using the length function, which gives us the length of a vector. And then we can return the harmonic mean, which is product to the power of 1 over n. So that's our geometric mean function. And we can compare and contrast that to the harmonic mean and the arithmetic mean. So it looks like in this case, for the numbers 1 through 50, it's a little bit closer to the arithmetic mean than the harmonic mean is. And if you want to see it with the log and the exponential way, let's see. It's the exponentiation of the arithmetic mean of the log of the values. So exponentiation of the arithmetic mean of the log of all the values. So this would also this would also calculate the geometric mean. Great. So now we'll look at conditional execution and how we can use warnings and errors in our code. So we saw this a little bit earlier in the activity, and if and an else statement, not an elf statement, else. So an if else statement allows us to conditionally execute code and then to supply alternative code if the condition is false. So you don't actually have to have the else part. You can just have an if and execute this code if the condition is true, and then just keep on going on your merry way. But else's are useful because then this is executed if this condition was false. Okay. So we'll use an if else here to create a function called calc square root, calc squirt, that calculates the square root of a non-negative number, but returns NaN, which stands for not a number in R. It's kind of similar to NA values in that they're contagious, but it's not exactly the same. So you can do 5 plus NaN. That's still not a number. It's kind of like infinity or negative infinity, I think. But there's other ways that not a number can show up, like the square root of a negative gives you not a number as well. So an imaginary number. Okay. So yeah, let's copy this code and see how it works when we, let's see, we're on conditional execution warnings and errors. Let's make that a section in our code here. There we go. Copy this. Okay. So if we run this code, you can see it calculates the square root of 4. So when it went through this code, it checked, is the value greater than or equal to 0? 4 is, that is true. So it returned our value to the 1/2 power, which is the same as the square root. When that value is not true, it prints a warning and returns NaN. So we can see if we tried to calculate the square root of -9, we'll see that it returns NaN and prints a warning. Let's see what the warning looks like. I guess R markdown. Oh, because I have the, if you have the warning equals false option up here, that it suppresses the warning we just created. So it makes it, we don't get to see it. Fix that in the global chunk option. Okay. And we can see when we try to calculate the square root of -9, it prints our custom warning that we put here. Okay, so you could put whatever you want here. You could say, you know, you're an awesome R programmer, but this shouldn't be done here. Something like that. You know, you get to customize it. So. So it looked and checked if the number was greater than or equal to 0. For -9, it saw that was false. So then it moved on to the else portion of the code and evaluated this instead. We can also chain multiple if-else conditions available, and R will progressively work through the conditions until one is true. As soon as it hits one condition that's true, so if the first one's true, it evaluates that, but then skips to the past all the else's. So if condition 1 was false, it would skip this. If condition 2 is then true, it would just evaluate this and skip this piece of code here. Okay. So we can look at that in this food type function. Oops. So let's copy this. So create function to determine type of food. Okay, so our function is not super useful, but it'll cover some foods. So we're writing our function so that it'll check first if the input string, which should be the name of a food for our function, if the input string is an apple, orange, or banana, it'll return that, hey, that's a fruit. If neither of those are true, then it'll check, is it a broccoli or an asparagus? Then it'll return vegetable. Otherwise, it's just going to say something else. So we can see what happens when we try it below. Maybe we'll paste it into the console so it's more clear. So it detects that broccoli is a vegetable, bananas a fruit, and Reese's Puffs other. Okay, so we can use the if else's, these change if else's to consider many different cases for what our function ends up doing. All right. So a little bit more here about conditionals. Let's next look at how we can make a function called is.wholeNumber that checks if a number is a whole number or not. So let's make a new chunk for this one. Oops. So we're going to call our function is.wholeNumber. This is sort of mimicking, there's some R functions that are able to check if things are certain types. So there's like a is.na function that can check if something's a missing value or if it's not. There's also a is.integer function in R that can check. Oh, that's why you have to put the capital L there to explicitly make it an integer in R. Otherwise, it thinks that's a double. But with the string, the number 5, it does not work. Okay. So we're kind of mimicking these other functions that already exist. Is dot integer. Oh, there's an is dot numeric. That would return true for the number 5. We're making one that's is dot whole number, where a whole number is -1, 0, 1, 2, all these round. These are in mathematics, these are referred to as whole numbers. Okay. How can we write a function that takes x and determines if x is a whole number or not? This might take a little bit of thought. So maybe I'll give you, let's pause the video and think about this for a minute or so. How could we do that? So there's not one right answer here. But one way you could go about this is using the round function. So the round function rounds a number to the nearest whole number. So we could create a variable in here called rounded that rounds x. And then we could check if x was equal to maybe we'll call it rounded x. If it's the same as the rounded version of x, then it's a whole number. Because we can see here, like if we round 7.9 to we get 8. And if we round just the number 7, we get 7. So if it's a whole number, the rounded version of itself is the same. So that would be a way we could write that function. An alternative way, you can also use these floor and ceiling functions, which also essentially round the number x. The floor function rounds x down always to the nearest integer rounding down. So maybe we'd call it like floor x. But that would end up working the same. Either way would work. I think the round one is makes more sense, so maybe we'll stick with that. But that's an alternative, just so it's out there. So yeah, let's check this out. So how about we'll write sum of the number pi, 3.1415. Ooh, not a whole number. Shoot. What about just the number 3? Yay, that returns true. Okay. Okay, so let's create another function. The caret operator raises a number to a specified power in R. So we're going to create a function that raises a number to a specified power. We'll call it maybe raise power. I guess up here, notice we separated the words with decimals, with periods. R allows that. Most other programming languages do not. So actually, I'm not a big fan of that. But so we'll maybe call it is underscore whole number. We'll use snake case here. Okay, there we go. So raise power. We'll say x and then power. So we want it to raise x to a certain power, but to return a warning if the number is negative. Otherwise, just return and an NA value if it's negative. Otherwise, just return the power of the number. So we'll use an if-else statement here. So maybe pause the video and try it on your own, and then we'll look at it together here. Okay, so to try this, we're going to use an if and then an else. So we set it up here. Inside the if, we'll put the condition. So if x is negative, if it's less than 0, return a warning and return the value NaN. So we want the warning to say, oh, it's got it in here. Careful. That number, I don't know, maybe instead of careful, we'll say check yourself before you wreck yourself. That number is negative. Okay, we'll be being sassy with ourselves when we try to use our function here. Okay. If it's greater than or equal to 0, which we don't have to explicitly put the condition here, because that's the opposite of this, we'll say return x to the given power. And I don't know, do I say specific values to try out? Oh yeah. Let's try it with these numbers. So calculate 2, 3, 4. There's 4 things here. So we want to calculate 4 to the second power minus 9. Oh, and the power is not a whole number. Oh, we got to use our whole number function. Whoops, I was mistaken. Okay, so I'll still finish typing this out here though. Minus 3 to the 1/3. Okay, so yeah, you may or probably had noticed my mistake. So I only checked if the number was negative, but we need to check if it's negative and the power is not a whole number. So we can do that using and. So you can call functions you created inside other functions that you're creating. So we'll say and then we'll enclose this in parentheses, and this equals false. So if x is negative and it's not a whole number, we'll say that power is negative. So let's see how this looks when we run this code now. Oh, gotta run this code first. So for 4 to 2, it does 4 to the second power, minus 9 to 2, no problem. 3 to the 1/3, sure. but minus 3 to the 1/3, doesn't like that. Okay. Now, some of you, if you're math majors or have some experience with math, you might be crying foul here, saying, hey, wait a second, minus 3 to the 1/3 power is totally a number. And you are correct. So, this is just what we wrote our function to do, although technically, it's more of like a math concept thing, but minus 3 to the 1/3 power is equal to 1 over minus 3 to the 3rd power. Which is actually equal to this. So really it is a number, but in R, if you directly try to calculate minus 3 to the 1/3, it quits and just says, no, that's not a number, even though mathematically it's equal to this. But I don't want to get bogged down in the math details here, though, so we won't worry about exponents, but just pointing that out. So this is our raised power function that we made that uses our whole number function inside of it. So often as you get more experienced in R, you'll be creating multiple functions, some of which you call inside of each other like that. Okay, and then some of the last couple things we'll look at is the if-else function and then logical operators. So the if-else function, which we sort of saw earlier a little bit, allows us to conditionally return a specific value. Typically when it's a single number or vector. Well, it's only if it's a single number or vector that you want to return into an object. Let's look at the help file again for if-else. See this? And then if you see these two things show up, you click on the one from base R right here. Okay. So if-else, to demonstrate it a little bit. For example, if we have like a vector of x's and say it's got the numbers -2, like this. If else, we could say like, oh, if the value of x is positive for each entry, return its value, otherwise make it missing. Okay. So if else is useful for potentially reassigning values in a way, to do many different things, but it works a little bit differently than a separate if and else. It's its own function for returning values given a certain condition, whereas this if and this else is for executing code. We can't put inside the if-else function, we can't put executable code here. It's just values to be returned. Okay. All right, so let's create a new, let's copy this code and use it to calculate the sum of 13 and 1989. So we can see, it calculates those numbers just fine. We can calculate the sum of NA and 1989 as well. Okay. It's very similar to what we already saw earlier in the activity, but just talking a little bit more in depth about it. So the default argument is NA remove equals true, but we can override that if we wanted to. By saying false. And then we use if-else statements in here to keep the numbers that are not missing as themselves, but if they are missing, this sets them equal to 0. Which is an assumption in itself. This is essentially assuming all missing values are zeros. In general, that's not a safe assumption to make, but that's what we're doing here in this function. All right. Okay, so lastly, talking about some logical operators in R. We've already seen this is called the pipe symbol, not to be confused with this pipe, which is the pipe operator. This pipe symbol is used in logical or Boolean expressions as an or, and the ampersand is used as an and. If you have a double version of the symbols, so 2 pipes or 2 ampersands right next to each other, these are what we call not vectorized symbols, not vectorized tools for checking logical expressions. So when I say vectorized, I mean that we can check if the number 5 is equal to the number 5 or a single other number. Okay, but R also allows us to check if entire vectors are equal to each other. So we can check if the vector 1, 2, and 3 is equal to another way to make the vectors 1 through 3. And it'll check each value of the vector, checking the equality between the two. And those were equal, those are all equal right there. And also check like this. You can go backwards with that vector, and then only the middle one is true because of that. So this is a vectorized operation because it can work across all the values of an input vector. When you do the double pipe symbol like this, or the double ampersand, this is only to be used for checking a singular value. Okay. So for example, we can use that here in this way because we're only checking if one condition and another condition are true, or another condition are true. Logical operators. Is that what we call this section? Yeah, logical operators. So is 3 less than 5 or -1 greater than 0? That's true because 3 is less than 5. So the or, we just need at least one of the conditions to be true. Is 3 less than 5 and 1 is less than 0? Or 1 is greater than 0? No, because this requires both conditions to be true since it's an and. Okay. Note that you would get the same, like we've been using a single ampersand and a single pipe operator or pipe symbol. Those also give you the same results, but these can be used to be vectorized across an entire vector of values, whereas these ones cannot. Okay. So let's see. Yeah, so here's some vectorized examples where we use the single ampersand or single pipe. Okay. All right. So it checks each value on each side and pairs them up individually and goes across the whole vector of values on both sides. Let's see. Okay, so let's try and create, it's the last couple things we'll do here. Let's try and create a function that takes a numeric vector as input and returns a Boolean or logical value indicating if the vector has any negative values or not. Okay, so we're going to use a new function here. Numeric vector, any negative. So we'll call this like any negative. And let's see, what do we want to call our input? X's maybe. It's going to be just a vector. Or maybe we'll call it numbers. So the any function in R is pretty helpful. Given a logical vector or a Boolean vector, is at least one of them true? Any will tell us if that's the case. So numbers, we can see is numbers less than 0. We had like the numbers -3, -2. We can check if that vector is less than 0, and we'll get a Boolean vector as the result. So using that here, we get a bunch of true falses, and then we can say, all right, any of these true. So we're using this vectorized less than symbol to create this function to check if any values in a given vector are negative or not. We'll make this an explicit return here, even though it would work fine without the return there. And then I think we can try this. Yeah, let's try it out on some values. So, or on some vectors here. So we can say 1, 2, 3. Hopefully that returns false. Hey, our function works. At least we think. What if we threw in a -1 in there? Hopefully that returns true. Yay, okay. Looks like our function works. Let's try to break it one more time. What if we threw in a 0? All right. Cool. Checks out. Okay, last thing. Does this code produce the same result as this? Which code appears to achieve its more intended purpose? Okay, so here I'm really isolating the issue of using a vectorized operator or not. So let's look at what this code gives. And then what this code gives. This one returns this. This one returns just a single value. So when we look at what's on each side, we have a vector of 4 values on each side. With the double equals, it's only taking the first value from both vectors and just comparing those. It's saying if both those are true. So this one only looks at first value in each vector. Whereas the top code here looks at all values in both vectors. So which one gets the thumbs up here? This one. Okay. We want, if we're comparing two vectors like this with a operator in between, you want to be comparing all the values. That's why we have the vectors in the first place. So this code is misleading and somewhat dubious in that it's only really checking the first values, but it doesn't return an error or a warning about it. It just only returns a single value. So it might give misleading results. So this is bad. Give that thumbs down emoji. Yeah. And yeah, you can paste emojis in your R code, which is actually kind of fun sometimes. Okay. So yeah, so that was the last function that we created and we looked at there. There's this bonus problem, which I'll let you try on your own. But yeah, that is an introduction to fundamentals of functions in R. We'll knit this one time. Here, let's see, MySum. Here, yeah, here's the problem. So we'll knit this one time. Make sure you didn't have any other errors. Perfect. Okay, great. So that is a activity covering fundamentals of functions in R. Thanks.